gravimetric analysis. Gravimetric analysis is a quantitative method that determines the amount of an analyte by converting it into a stable, pure, and weighable form. It is one of the most accurate and classical techniques in analytical chemistry. Now, let's take a look at basic steps in gravimetric analysis. There are 7 basic steps. First, dissolve the analyte in solution. Second, precipitate the analyte as insoluble compound. Third, digest the precipitate to improve purity and size. Fourth, filter and wash the solid to remove impurities. Fifth, try or ignite the precipitate to constant mass. Sixth, weigh the final product. And lastly, calculate the analyte amount using stoichiometric formula. Next, let's go to types of gravimetric methods. There are 2 types of gravimetric methods. First, precipitation gravimetry. The analyte is turned into an insoluble solid. As example, chloride ion to silver chloride. Second, we have volatilization gravimetry. The analyte is volatilized and collected. As example, water content by drying. Now, let's take a look at advantages and limitations. There are some advantages and limitations in gravimetric analysis. For the advantages, it is high accuracy and precision. It is also requires simple equipment and procedures. And the results are easy to verify and reproduce. But for the limitations, the time-consuming process is very long. It is also requires complete and pure precipitation. Thirdly, it is not suitable for very low trace concentrations.
Let's begin with the sample preparation, which is the foundation of accurate gold analysis. First, we start by crushing and grinding the ore or sample material to a fine powder, typically to a size of 100 to 200 mesh. This increases surface area and ensures the gold particles are fully exposed for digestion. Next, we use proper sampling techniques like refill splitting or cone and quartering. This step is critical because gold distribution in ores can be uneven. So our goal here is to take a small yet representative portion of the bulk sample, usually around 0.5 to 5 grams. After that, we dry the sample at around 105 to 110 degrees Celsius. This removes any moisture that could interfere with weight measurements during the gravimetric process. Accurate weighing is essential, especially because gold content is often calculated down to microgram levels. Once we have dried the powdered sample, the next step is to dissolve any gold present using a chemical digestion process. We use a strong acid mixture called aqua regia, which is a combination of 3 parts hydrochloric acid to 1 part nitric acid. Aqua regia is one of the few reagents capable of dissolving metallic gold. We add the aqua regia to the sample in a beaker and gently heat it. The nitric acid oxidizes the gold, and the hydrochloric acid form soluble gold complexes, primarily chloroauric acid or HAUCl4. You will notice brown fumes of nitrogen dioxide being released during the reaction. So, it is important to perform this step in a fume hood due to the toxic gases. Once the reaction slows down and no solid particles remain, we know that the gold has gone into the solution. At this point, we filter the solution to remove any undissolved impurities, ensuring that the gold remains in the clear solution as a chloride complex. This solution is now ready for the precipitation step, where we will selectively reduce and recover the gold as a solid using SMB that will be explained on the next slide.
Next, a chemical called sodium metabisulfate, also known as SMB, is added slowly into the gold solution. SMB acts as a strong reducing agent Its main function is to convert gold ion, specifically Au3+, back into metallic gold in its neutral form. This chemical reaction is important because it changes the dissolved and invisible gold into solid particle that can be seen. As the SMB is gradually added, gold begins to precipitate from the solution, forming a brownish or sometimes dark orange solid. This visible change confirms that the gold ion have been successfully reduced into their metallic form. Once the gold has fully precipitated, the mixture is poured through a filter setup, usually filter paper placed in a funnel. This process separates the solid gold from the remaining solution. As the liquid passes through, the brown gold particles stay on the filter paper. At this stage, it is important to be gentle to avoid losing any fine particles of gold. The collected gold solid is now ready for the next step, which is rinsing with distilled water to remove any leftover impurities.
After we filter the gold from solution using filter paper, some impurities such as chloride ions, neutral ions, or leftover acids may still remain with the gold. This can affect the final weight and also can lead to inaccurate results. To remove these impurities, we wash the gold using small portions of distilled water. We do it carefully and gently, pouring the water around the edge of the gold, not directly on top, because we want to avoid losing any particles. Last but not least, we need to check the cleanliness. To check if all the chlorides are removed, we can test a drop from the washing water using silver nitrate. If there are any white precipitate forms, that means there are still chloride ions inside. So we need to keep washing until there is no precipitate forms.
Here is the procedure for drying the gold bead is typically carried out. First, preparation of the gold bead. Carefully transfer the tiny gold bead from the vessel where it was washed into a clean, dry, and pre-weighed porcelain crucible or a fresh cupel. It is crucial to ensure no loss of the bead during this transfer. Sometimes the bead is already in a small porcelain crucible for the parting step, which can then be used directly for annealing. Second is heating or annealing. Gentle heat source. The crucible containing the gold bead is then subjected to gentle heat. This can be done using two methods, which is first a muffle furnace. Placing the crucible into a preheated muffle furnace set to a moderate temperature, typically around 600 to 800 degrees Celsius, well below gold's melting point of 1064 degrees Celsius. And second is Bunsen burner or torch, holding the crucible with tongs over a low Bunsen burner flame or a small torch. The key is to apply gentle, even heat. The third procedure is cooling. So in this procedure, I will share you about two important things. So the first one is control cooling. After heating, the crucible containing the annual gold bead must be allowed to cool completely. This is critically important for accurate weighing, as hot objects create convection currents that interfere with balance readings. Okay, the second one is desiccator. The cooling should ideally take place in a desiccator. A desiccator is a sealed container that contains a desiccant like silica gel to maintain a very dry atmosphere. Cooling in a desiccator is to prevent the gold bead from reabsorbing any moisture from the ambient air as it cools, which would again lead to an inaccurate weight. And the last procedure is wigging. Okay, once the gold bead and its container have cooled in room temperature inside the desiccator, they have carefully transferred to a highly sensitive analytical or microbalance for precise wigging. By following this carefully annealing procedure, analytes ensure that the measured weight truly represents the pure gold content, free from any interference from moisture or surface contaminants.
In short, we first dissolve the sample in acid to get all the gold into solution.
Then, we use a chemical reaction to turn the gold into a solid form. It is often as gold metal or gold compound. After that, we filter, dry, and weigh the pure gold.
Since we know the mass of the final gold and the mass of the original sample, we can calculate the gold content.
Gold is one of the most valuable elements on Earth. Accurately determining gold content is essential not only for fair trade and proper refining, but also for quality control and environmental responsibility across industries.